The next intermediate that we will be looking at are carbenes. You will recall the last set of intermediates we looked at were radicals, which were essentially a atom that has an odd electron, carbon, or it could be oxygen or a halogen. In this lecture, or the next couple lectures, we will be looking at carbenes. In this one, however, we'll be looking at the structure of carbenes. What are carbenes and what is the actual structure of these carbenes? Next, we will look at how they are generated, what type reactions are used to make carbenes, and how are they made as intermediates for different reactions. So let us start by looking at a reaction that we've all seen before, and that is the Simmons-Smith reaction. You will recall it's an alkene reacting with diiodomethane in the presence of zinc, copper, and we get here the cyclopropane, so we can transform the alkene functionality to the cyclopropane. Here's another example. Here's the alkene reacting with the Simmons-Smith reagent, and we have here the cyclopropane. Let's see how that happens, or what is the actual intermediate. The actual intermediate, as we'll see in a second, is carbene. So what are carbenes? Carbenes are neutral carbons. Notice neutral. So in other words, compared to the radicals, which has an odd electron, and as we'll see later on, the carbocation, which has a positive, and the carboanion, which has a negative, carbenes here are neutral. They have two atoms bonded to the carbon. And in addition, there is a pair of non-bonding electrons. So here's an example. So here's a carbon. It has, in this case, it's bonded to a hydrogen and another hydrogen, two bonds, and there are two electrons. As you can imagine, there are various ways of these electrons can be organized. One way is a pair in an orbital. So they are paired. The key word here is the electrons are paired and in one orbital. And that's called the singlet carbene. As you can imagine, the triplet carbene has the electrons, the two electrons in two different orbitals. So notice here that the orbitals, the electrons can have opposite spins or similar spins. So here they have similar spins and here they have opposite spins. So these are the three, well, essentially two types of carbenes, the singlet and the triplet, but the triplet has two possibilities. For our study, however, we will concentrate only on the singlet. So in this course, we will concentrate only on the singlet carbene. So let us examine what that looks like from the atomic level. So as you know, carbon has 6 electrons. So you look at your periodic table, you will see that carbon has 6 electrons, and of those 6 electrons, 4 are valence electrons and 2 are core electrons. So how are these electrons arranged in the carbene? As you can see here, there's a bond, and there's a bond, and there's an orbital for the electrons. So we need 3 orbitals. We need 3 orbitals. You will recall that the carbon has Let's write it. 1s2, 2s2, 2px1, 2py1, and 2pz0. So that's the atomic configuration of carbon. Carbon has 6 electrons. So what we need here is to form 1, 2, and essentially 3 equivalent orbitals to put electrons that can be bonded to another atom, and the pair of electrons. That would make it an sp2. So here we're mixing here s and 2 of the p orbitals. So we have sp2, sp2, and essentially another sp2 that we call a sigma orbital. So we have 6 electrons, so it's 1, 2, 3, 4, 5, and 6. Notice the unhybridized p orbital right here has no electrons. Of equal importance here is this gap, delta G. If this gap is pretty large, these electrons will be paired. In other words, these electrons will be paired in the carbene. If it's small, if the gap comes down to here, for example, then that's where you can imagine we'll have the triplet carbene, where this electron goes over into the other orbital. But for our course, we will look at the singlet carbene, and this delta G here is large enough. So this delta G here is large enough so that the electrons are paired as shown here. As you can imagine, this electron forms a covalent bond to another atom, and this electron here forms a covalent bond to another atom. So that's essentially the structure of your singlet carbene. Let's look at factors that can stabilize the carbene. If there is an atom that has at least one unshared pair of electrons that's bonded to the carbene, as you can see here, it can donate its electrons to the carbene, hence stabilizing it. Another aspect here is if there are a lot of unshared pair electrons on the atoms of the carbene, due to electron repulsion, we do get this type geometry here, which is more sp2 like, where these electrons try to stay as far apart from each other as possible. Bottom line is that the singlet carbene is stabilized by atoms adjacent that has at least one pair of electrons, as we can see here in these diagrams. Generation of carbenes. Now let's see how are carbenes formed. Here's one way. There are many ways. We'll look at quite a few, but here's one. If you have here a carbon that has a leaving group, notice here chlorine is a good leaving group because after it has left, it has an unshared pair of electrons, and of course chlorine being electronegative, it can stabilize that unshared pair of electrons. If this carbon also has a hydrogen, it's possible to use a strong base such as tert butoxide as a strong base. As you can imagine, it's a strong base because its conjugate acid is tert butanol, which is a weak acid, so you'd expect its conjugate base here to be extremely strong. This extremely strong base can pull this hydrogen off as a proton. Notice, as a proton with a positive, which means these electrons here now go on to the carbon. That makes it a carboanion. Since we have chlorine, which is a good leaving group, it can leave with its bonding electrons. We should really have the bonding electrons around it. And this is a weak base, or pretty stable, makes it a good leaving group. And what's left behind is, of course, our carbene. As you can see here, we're leaving out the non-bonding electrons, but they are still there. And as you can imagine, as we have discussed from the last slide, that makes this carbene here a singlet carbene and pretty stable, well, fairly stable. Let's go back to the Simmons-Smith reaction here. So, as we pointed out, one of the reagents is diiodomethane. So here we have an iodine, and two hydrogens. Let's see how it works. Here's zinc. Of course, as you know, if you have a bond such as a carbon iodide bond, and you have here a metal such as zinc, it can be inserted right in here, similar to the Grignard type reagent. Remember, the Grignard reagent is the insertion of magnesium into a carbon halogen bond, typically bromine or iodide or chlorine, but not fluorine, just too reactive. Same thing happens here. Zinc inserts itself right into this bond here. The result is that zinc, being more electropositive than carbon, so if you look at your periodic table, you'll see carbon to the top right compared to zinc, which is down in the transition metal. So this carbon here is more electronegative than the zinc, as shown here. So it acquires a partial negative charge. And as we know here, iodine is a good leaving group. If it leaves, it will leave as I-, very large, and it can accommodate that negative charge. So what we have here is a carbene-like. That's why it's called a carbenoid intermediate, as opposed to a full carbene. So this is your carbenoid intermediate. Let's see why again. This carbon has partial negative, really two electrons. In other words, these two electrons here are very close to that carbon, and this being a good leaving group has the potential to leave in a reaction. So the reaction of this carbenoid with an alkene such as this will give us here the cyclopropane as shown here. So these would be hydrogens when this reacts with the alkene. So that's the Simmons-Smith reaction. Let us look at another method to generate carbenes. And this is the decomposition of the organometallic again. So notice the organometallic is coming back here. Organometallic, of course, as you know, organo means carbon. Hydrogens, metallic here means non-carbon. Typically your transition metal type. So here we have carbon tetrachloride bonded to a silicon. So this silicon here is bonded to this carbon, and it has 3 chlorines bonded to it. In the presence of heat, we get SiCl4 and our carbene. Here's our carbene. Should really have 2 electrons right here. Same here. So this carbon here is bonded to this phenyl group here, and of course we have our mercury that's between that CH bond. And of course, in the presence of heat, we get our carbene here and another product here, the metallic product. So let's go back to this reaction and see in a little more detail what happens. So this is SiCl3, here it is, and this is this carbon right here, and it has 3 chlorines, 1, 2, and 3. As you can see here, silicon trichloride, if it gives up its electrons to this carbon and this leaves, you can see you have your carbene. So this will leave as Cl minus, and this will come in as SiCl3 plus. So as you can imagine here, the combination of this gives SiCl4 and of course our carbene. Similarly, you should be able to work out a similar type mechanism or understanding of how this decomposes. Notice much less lower temperature to give our carbene here. Let us look at another method here, and this is the decomposition of diazo alkane. You may recall your diazo group looks like this. So this is your diazo alkane here. It's a neutral molecule, but it has 2 opposite charges as part of the molecule, as shown here. The nitrogen here acquires a formal charge of -1, and this nitrogen here, because it has 4 bonds to it, has a formal charge of +1, but the molecule is neutral. Resonance structure here, as you can see, these electrons can come in, and these electrons go out here to form here the anion on carbon, and here the nitrogen is positive. As you can see, this looks pretty much like nitrogen gas. So if these electrons here come in, we have our carbene and nitrogen gas. Notice again, it's nitrogen gas. So this is a real driving force for this reaction, because any reaction that gives off a gas as a product is entropy favored. And so this is a very favorable reaction because nitrogen gas comes off, and here is our carbene. Here's a more specific example. So we have here our diazo alkane. We can do the same here. These electrons can come in and here, and what we'll have here is our nitrogen type right here, and then if they come back out, we have nitrogen gas and our carbene. So again, you should be able to use resonance here to demonstrate how carbenes are formed and how the nitrogen gas comes off as a product. Another type compound that can be used to generate carbenes is the dialkyl diazurine. The diazurine. Here is the structure. It's a nitrogen-nitrogen double bond in a 3-membered ring. As you can imagine, it's very, very unstable because of the steric strain that's here. But let's see what can happen. Here we have nitrogen-nitrogen double bond. If it gains another bond, or 2 electrons, as shown here, we have nitrogen gas potential, and of course this leaves, and we have here the carbene. So this will give it the positive charge by these coming in, and this will put back the electrons here, and this comes off as nitrogen gas. So that is another method of making carbene. And notice here they all use energy, in this case light, to get this reaction going. Here is another type reactant, and this one is a ketene. Notice the name of this molecule, a ketene. It's a carbon-carbon double bond bonded to an oxygen double bond. That's a ketene, not a ketone, but a ketene, because of this double bond here. In the presence of light, as you can imagine here, these electrons come in. So now this would look like carbon monoxide, and then these electrons go here to form our carbene right here. So here's our carbon monoxide coming off again as a gas driving force, and we have created here our carbene. Another functionality here is alkene. As you can imagine, lots of heat because alkenes are fairly stable. But let's see what can happen. 2 electrons off the double bond goes onto this carbon, and the sigma bond electrons go onto this carbon. So when these 2 electrons move over here, this becomes negative, this becomes positive, and these electrons move over here to create the carbene, and this portion here will be the other carbene. So we have in essence created 2 moles of carbene here. As you can imagine, it works best, or it's of use if this is a symmetrical molecule where the R's are the same, so we don't have mixed carbenes. Here's another type molecule that we have here, and this is an oxyrane. You may also recognize another name for this is an epoxide. So here again we have a similar type reaction. So here is a carbon, here's a bond, and a bond to oxygen. So as you can imagine here, if these electrons here, 2 electrons, go to form a double bond here to this carbon oxygen, creating a partial positive here, or a positive, and then these electrons come in, we have our carbene, and of course we have our ketone. So this would represent the ketone portion, and this would represent here the carbene. So again, in the presence of energy, in this case light, to generate our carbene as a product here. Let's look at this one, cyclopropane. Same type reaction. These electrons can come over here to form here our alkene, then these electrons here can go onto that carbon, which was positive because of these electron movement, to form the carbene. As you can see here, it's best to have fluorines on it because of the stability gained from the non-bonding electrons for this type carbene over here. So in other words, this is not a reaction that will readily occur for your typical propane, cyclopropane, but for this particular one where there are atoms that can stabilize the carbene, that's very favorable. Let us look at, I think this is the last reaction here, and it's a very important one because it's a bit of chemistry here that we've seen before. So here is a tosyl hydrozone. So tosyl hydrozone, you may recall this is the tosyl group right here, and this is the hydrozone right here. In the presence of a strong base, notice this is a strong base, butyl lithium. Why is it a strong base? Because butyl lithium, the conjugate acid of the butane anion, is butane, which is a very weak acid, as you can imagine. It's an alkane. So the conjugate base here, Bu minus, is an extremely strong base. Of course, the counter ion is lithium. So in the presence of butyl lithium, we have this and nitrogen again. Notice nitrogen, as you can imagine, it would come off based on this, and our carbene right here. Let's see how that happens. So butyl lithium, which is a strong base, will abstract this hydrogen here because it's relatively acidic. So the electrons are left behind. The bonding electrons here are left behind. As you can imagine, we have quite a few arrow movements here, but hopefully you will understand. These electrons come in here, these electrons go onto this carbon, as we've seen before. So this would be a double bond based on the resonance, and then these electrons come out to give nitrogen. So let's do this. So this comes in here, this goes over here to get that. Okay, I think I see what's happening here. Let's take that out. So let's go again. So these electrons come in here, and these go onto this carbon to create this, a resonance structure. So this is really a resonance structure right here. Then, as you can imagine, these electrons from this bond come back to form this nitrogen here, and then these electrons go onto the sulfur to form that salt right here. So here's the salt, and of course this is our carbene generated from that. So that is our carbene that's generated from a tussle hydrozone. We will see quite a bit of this reaction when we start looking at the reactions of carbenes, because we'll make the carbene from a compound like this, and it will react with another reagent to give another product. I think this is the last, no, this is not the last slide. Let's look at one more. So here's an example of what we did before. So here is a hydrozone. So what we have is the nitrogen, and the tussles is a tussle hydrozone, as we've said before. Butyllithium, acidic, takes that off to put the electrons right here. These electrons come in, go on to this right here. Then we have these bonding electrons come back out, and these bonding electrons go onto the sulfur, and we have nitrogen gas, and of course here is our carbene. So this carbon here is divalent, 1, 2 valent, and an unshaded pair of electrons. In this case, more than likely a singlet carbene that's generated from this type molecule. What we'll do in the next lecture is to carry out reactions of carbenes. So I think this is the last slide. Yes, it is. So so for this first lecture here on carbenes, we just looked at the structure, and for our course we're looking primarily at the singlet carbene, and we have also concentrated on the generation. How are these carbenes made? So in the next lecture we will look at the reactions of carbenes.